with the later. And next up, we have Murray Thompson from Cefas, who I think is probably quite a nice segue from the previous talk into this one, looking at marine food web indicators.
Brilliant. Yes, thank you very much. So I'm working in the Pyramids Life project. I'm based at Cefas. I'm going to talk through developing a food web indicator, a marine food web indicator. I did this work with Chris Lynham, who's also at Cefas, and Izaskun Preciado, who's in Santander at IEO. So I should, a disclaimer before I go any further, I built my career around something kind of ridiculous, but also a little bit gruesome. That's studying fish stomach contents or stomach contents of animals. And I started actually by looking at midge larvae. So I was dissecting midge larvae, looking at diatoms in their stomachs in Iceland. I've since moved up the food chain. I'm now looking at fish, and next will be mammals. Who knows? Right. So the existing OSPAR food web indicators, we've got 4 really that look at food webs, or supposedly look at food webs. We've got the larger fish index, which Lorna presented earlier, and the size composition of fish communities. And they're both these size-based indicators. And you can see they don't use any species information. So that's my kind of infographic on the right, left. And then we have the mean maximum length of fish and the average trophic level of marine predators. And that's on the right here. And these are kind of species-based. So each species gets a single value. And these indicators, they're very good at looking at impacts of fishing, but they kind of miss key food web properties that I was really interested to try and build into an indicator. So who eats who and where? There's some really key things that are kind of missing from this. So I was trying to bring these kind of data together and synthesizing size information, so body size information, species information, and their diets or their sort of stomach contents data to try and get a picture of these kind of ecological pyramids that the project's about. And doing that, we want to bring in properties that we know are really important for food webs. So that's predator-prey mass ratio, so the difference in size between predators and prey. We know that's a key property in controlling energy flux through ecosystems. And like I said, who eats who and where? So actually how much food comes from the plankton pathway compared to the benthic pathway. So to do that, we need to draw together lots of stomach contents data, this is what I like. So we got together across 15 different organizations across the North Atlantic and Arctic. And that involved 8 countries. So Iceland, Spain were a big part, NOAA in the US. And now we've got a data set containing over 1.7 million observations from fish stomach contents, with hundreds of predators and thousands of prey taxa. But we needed some new science because the way the data had been collected and reported, they had some really important differences. So sometimes there was prey occurrence, sometimes counts, sometimes biomass. And that was a bit of an issue to make comparisons effective across these different ecosystems. So the new science we developed was we use predator-prey scaling relationships to predict this missing data, as it were. So we had 45% of the data were missing some of this information. So when I say predator-prey scaling relationships, what I mean is we predict the biomass inside a fish stomach using the taxonomy of the predator, their body size, and the prey functional group. So is it a zooplankton or is it benthos or is it fish? And you can see here the models. The grey dots are all the data. The blue dots are the actual empirical observations, and the red dots are our models. And you can see that our models are actually really good at recreating some of the observations we were seeing. So they seem to be working really well. And the important thing to take home from this is, first of all, you can actually predict, if you have a species and a size, we can predict how much zooplankton it might be eating or how much benthos it's eating. So this is really useful for food web modeling and understanding ecosystem and fluxes through ecosystems. The other key thing here is that a small cod behaves differently to a large cod, but also to other different species, right? So in these relationships, we found significant differences between all of them. So knowing species and body size information is really useful to bring together and quantify this. Okay. Oh. So the next thing we had to do was test which approach is the best way to classifying feeding gills. And there's been a few that have been published before. So one of them, a key one, came out in 2000 by Lance Garrison and Jason Link, and that was in the US. And they used biomass of prey taxa. One I published in 2020 was really using a prey occurrence. The reason I did it differently is because the data were different. We didn't have prey biomass, not in the same way. So this is where all the new science came in. And we developed a new method in the Euromarine workshops which was just using really simple traits. So how much zooplankton it is, how much benthos, and also predator-prey mass ratio and prey size. So I call that the simple method, right? And we wanted to test which one was the most effective. So which one could repeatedly classify the same species size class into the same guild. And the values, lower values here, so the lower values show the most robust approach to classifying feeding guilds, right? So they all perform better than random. So the random down here, but actually, so all the methods do better than that, but the occurrence seems to be the most robust. So that was useful information, but there was another key property we wanted. And I find it's quite hard to explain, but what we want to do is we wanted to compare the guilds across ecosystems. So we didn't want to be guilds to be really area specific. We didn't want a North Sea guild versus a US guild versus a Spanish guild. So I just plotted the data centroids of all the different methods. So what you want, a really ideal situation is we have all the guilds for a particular method really coming together around this data centroid. So that means your guilds really represent the data quite evenly across all the different ecosystems. So we found the occurrence method is actually really driven by spatial patterns in prey taxonomy. So that's not really a property we wanted. And so is the prey biomass approach. So we decided to use the simple approach, which we developed as part of this project. So this is just a plot just to show you what the simple, after the classifications through cluster analysis, what the different guilds look like. So we have a planktivore guild, which are they're the smallest body size, and they eat the most plankton, clues in the name. And we've got, they have the smallest prey size and the highest predator-prey mass ratio. At the other extreme, we have piscivores, which are the biggest, that take the biggest prey, that have the lowest predator-prey mass ratio and eat the most fish. Then we have these two intermediate benthivorous guilds, and this rather classically named pisco-crustivore guild, which is, okay, so they eat fish, a mixture of fish and crustacean. So then just to take you through the process of actually how we use this to look at change in food web structure and function. So they have lots of fisheries, so survey data, so otter trawl data over the Northeast Atlantic. And then we have stomach contents data, and both of those data sets we classify in exactly the same way. We categorized things by their taxonomy and by their body size. And then with the stomach contents data, we use the cluster analysis to define the feeding guilds. And then we merge those feeding guilds to the survey data using the taxa and size information. Then we sum the feeding guilds biomass by species and the biomass and the species. You either take a mean across these different assessment strata, or you look for temporal correlations to do this. And we also identify during this process, we look at, there's lots of fish have been sampled at very different levels. So there's lots of information on cod, very much less information on some of the more minor species. So here we have the top row of plots here to show how biomass is distributed as a mean, right? So you get planktivore biomass is typically higher in the Atlantic. Benthivorous biomass is highest in the sort of Irish Sea. Pisco-crustivore and piscivore biomass increases moving northwest. And the bottom row of plots show temporal change in these. So we have blue is down, red is up, and if it's got a black box around it, it means a significant correlation. And the key take-home message from this plot really is that a food web response in the Celtic seas, you can see decreasing planktivores, but increasing fish higher up, so pisco-crustivores and piscivores, and also increasing benthivorous in southern North Sea. And these have really coincided with big reductions in fishing effort. So we did these plots also for species richness, and this was really called for by both OSPAR and the MSFD and UK Marine Strategy, because they're really keen on having, firstly, 4 guilds, and also looking at change through time. So this is recently published in the OSPAR Policy Status Report. And I should acknowledge, actually, there was lots of contributors who are all working on the manuscript at the moment. So yes, lots of people helping out here. So the next thing we're trying to do is assess what the good environmental status looks like. So setting the thresholds like Lorna was talking about. This is something we're doing with modeling to see if you relieve fishing pressures and other pressures, what state would the actual ecosystem be in? And are ecosystems, different ecosystems, are their balances and feeding guilds different? So we're really exploring that at the moment. And thank you very much for listening.
Thank you, Mary. That was excellent and looked like a lot of work there in stomachs. I also learned something we have in common. We both work in chironomids in Iceland.